Okay, I have 8:30, so we can get started. So Monday was just the overview of the course, right? The logistics parts. This is going to be a similar kind of lecture, but not logistics, more what is the content that we want to cover. Right. So the big question that we should be able to answer at the end of today is, what is computer engineering? So I'll start off with just asking you guys, what do you think computer engineers do?
Design hardware.
Okay. What kind of hardware?
The dinner.
So they're kind of like on the hardware slash software side,
Uh-huh.
and they program like a little bit more lower and than regular software engineers, and they design like CPUs, just like IoT stuff.
Uh-huh. So along those lines, what are the skills that you need in order to design something like, say, a CPU?
You need to know computer architecture, you need to know software development. So there's different types, like maybe like web development, depending on what you're doing, or
Uh-huh.
maybe like if you're like creating like a BIOS or operating system, like that.
Yeah. So you need to be aware of programming when you're designing hardware so that you can make sure that the hardware is efficient when implementing those programs, right?
Yeah.
So that goes to computer architecture, but underneath computer architecture, what is the base kind of knowledge slash skill that you need?
Different physics.
That's way down.
That's what we're looking
That's too far.
Circuits.
So what kind of circuits?
Circuits.
Digital logic circuits. So you need to know digital logic circuits. We need to know programming. What else do computer engineers need to know? So they do need to know physics just as base knowledge so that they understand in order to understand the digital logic part, right? But what else do we need to know slash what else do computer engineers do?
Schematics. Layout.
Yeah, so if you're given like a design, like block level, sure.
This is pretty broad, but I feel like there's a base in electrical engineering.
Yeah, so what in electrical engineering then? So digital logic is part of that. Yes?
Yeah.
So what else?
signals and systems.
Yes. So like you mentioned, we're designing systems, right, as computer engineers. And part of these systems, we need to be able to process signals. We need to be able to maybe generate signals. We need to know how to do digital signal processing. And a lot of the times you also need to know how to do analog signal processing. And also the conversion between the two. So digital to analog to digital. Okay. Anything else in electrical engineering or from computer science? Good coverage of what computer engineers do slash what are the skills that they need to learn, right? So what do we do, right? We are primarily, the biggest component is designing computers, right? So that would be like computer architecture, So CS 331, many of you have taken already. And then computer systems. So at the system level, and it also goes with embedded systems. That's also where computer engineers would be primarily focused. And in order to do these things, we need to know both hardware and software, like you guys mentioned. And also just designing hardware in general. So it doesn't have to be a general purpose computer, right? You can design a accelerator. So the big thing that we wanted to design accelerators for, and there was a huge increase in need for computer engineers, was not too long ago. What do you think? Lots of money.
Use.
Very similar to GPUs. GPUs. So you're going in the right direction, but think what real consumers were buying too. No, not CPU, but not CPUs. Hardware.
IoT devices, like little ones, I don't know what they're called.
So yes, that goes more towards embedded systems though. I'm talking about like a standalone hardware device that people were buying. Maybe not normal people, but people that maybe had sources of energy that was cheap. So mining,
Oh, like the Bitcoin stuff or whatever?
yeah. So that's why I say you're close with GPUs, because people did use GPUs. But if you wanted to be more efficient about it, you had what was called a Bitcoin mining ASIC. So an ASIC is an application-specific integrated circuit. So it only does one thing. You can't then take it out of your Bitcoin mining machine and go put it into a computer and use it for gaming or something like that. It only did Bitcoin mining. So there are examples like that too. You would need the know-how of both algorithms, because you're implementing the algorithm specifically with SHA-256 encoding, and you needed to know how to efficiently implement that into a hardware data path. And then beyond that, you also needed to know the VLSI, so very large integrated circuits. Okay, so there's kind of a broad range of things that computer engineers can do, but in terms of the skills, what you need to learn, it's going to be that intersection of computer science and electrical engineering. Okay. And we already talked about this a little, right? So electrical engineering, we need to know digital logic design. We need to know signal processing, not just digital signal processing, but signal processing. Those are our key components. And then in order to know these things, you needed to learn physics at some point, right? And from computer science, we need to understand the algorithms that we would be implementing or would be implemented on the architectures that we are going to create. And we need to learn computer architecture as a starting point, usually. But what you learn and the skills you gain from computer architecture will also be able to be applied to making things like those ASICs. And you need all of these skills in order to do something like an embedded system design. So hardware, software integration, and also creating a system to do a specific task. So what are embedded systems? Maybe we can start with what's an example of embedded system?
like those smart washers or like, you know,
Uh-huh.
the Samsung ones.
Yeah, so it needs some sort of computer in there in order to provide the interface for the user. And presumably it has some sensors to know like how much water is needed to do the cycle, is when it's doing the final cycle and it's trying to get all of the water out by just spinning very fast before it goes in the dryer, right? Is it sufficiently dry enough in order to go into the dryer next? And so you need all of these systems and you need some kind of computer. It's usually in a system like that, it's usually going to be a general purpose chip that has a program on it that's and it's going to be a low power one because the program can be pretty simple, right? So that is an example of an embedded system. Any other example of an embedded system? Yes. So very similar, right? So the computer in your car, what kind of sensors do you think it needs? Yep, tire pressure. Good. So oil level, I haven't seen a sensor for this. It's always the dipstick, right? But maybe that's something that could be implemented. Anything else? Well, actually, they need some kind of sensor to tell you to change your oil
Yeah.
because your car does. So maybe there's oil quality
Yeah, right.
sensors. Maybe not oil level. Any other examples?
Or satellites.
Satellites? Any other simple examples? I like a washing machine. What else?
There's a printer.
Yeah, a printer. It needs to be able to connect to the network, right? You need to provide that user interface to the user. It needs to know how much ink it has. It has to have all of these components. So designing a printer would be something a computer engineer could do. I keep looking at the vending machine out here. So the vending machine, right, it's an embedded system. It has a computer in it. Believe it or not, there is a computer in that thing. And then the user interface is just buttons, right? And it needs to know that the money is real. So it checks like either the size plus the weight of the coin, things like that. Or the scanner to scan the bill going in, make sure it's real. Okay. So now that we have examples of embedded systems, can we give kind of a definition to embedded systems?
System that uses a computer to do it.
Okay, we can start with that. Can we expand on it?
Lower level.
I feel like any computer system that is in something that otherwise wouldn't need it. Like,
Okay, so we do want to add on to that. What does an embedded system usually need to do? Like, why is a computer not an embedded system? Like a computer is.
Doesn't have sensors.
So that's a good starting point.
just because a computer can do multiple things.
Yeah. So a computer is like general purpose, right? But embedded system, what are you trying to accomplish? Like say with a vending machine? One task or few tasks. Okay, so it's very specific to what we're trying to do. Right, so a computer system designed to perform one or a few dedicated functions. And then we talked about examples already, but one thing that we haven't talked about are what are software that these systems run? Like what software do you think is on the vending machine?
Assembly.
So it's all of them, if they have a computer, is going to have some sort of assembly, right? So higher level, what's,
Usually C or C++.
uh-huh, what about lower level than that? So in between,
Like in Arduino software?
yeah, it could be Arduino. Right? So some small, very power efficient board is most likely in that thing, right? Same thing with the washing machine. So the software that they're going to run is probably going to be ARM or some similar ISA like that based, and they will have their own little small operating system, right? And what about a more complex embedded system? Like going back to the car, a Tesla is a little bit more complicated of a car, right? Because they implement some self-driving functions, right? So does anyone know what they use in terms of hardware to run that software?
They use like ultrasonic sensors around the car. They use the cameras.
Yeah.
Around the car to like detect what's around it. To like.
So in terms of sensors, you need some kind of sensor. And you're right, they used to use the ultrasonic sensors, but they have sense, even in the cars that have them, disable them. And they have switched to solely cameras. But what about the algorithm for the self-driving? What hardware does that run on? Any guesses? It's not going to run on Arduino, right?
Can it be something like dedicated to that specific thing? Or?
Yeah, so that could be an approach. And it is a smart approach, but the one reason that they don't do that is what happens to this algorithm, say, at least once every 6 months. It gets updated, right? So it gets updated, you have this specific hardware. I need a new Tesla to use the new software, right? So what else?
Is it a chip or?
It is a chip. It's something that you know about. For sure know about this.
You?
Very close to a CPU,
Oh.
not a CPU.
is it ECU?
So you guys are very, very
It's an
good.
ALU. Something like that.
It's a GPU.
GPU, okay.
Because I mean, it's mostly taking in camera data now, right? So images, square matrices, GPU. Right? So it's actually an AMD GPU that's in the Tesla. But it is a computer engineering task to figure out that the GPU was the best option, right? Because like I mentioned with the dedicated thing, we want to update our algorithm. So we don't want a dedicated hardware specifically for it. But we can't run it on CPU because it would take way too long and the system would just not be responsive. It would not work. Like it would figure out maybe 10 seconds later, oh, I needed to brake, but I'm already crashing. Right? So the GPU was kind of that balance. And something like someone mentioned TPU. Yeah, so TPU might be a good option too. Because what is a TPU? It's just a matrix multiplier accelerator, right? And that's what they really need from. And same thing with GPU. GPU is mainly a matrix multiplier, but the GPU is a little bit, has more general purpose to it than the TPU does. All right. So part of the software that is running on these embedded devices is the operating system. Right. So the operating system is going to be the interface between the hardware and the user and it's going to manage your resources. So the other thing is it's going to ensure real-time results in some cases. So going back to the Tesla, we want real-time results for the autopilot, yes? So the operating system on the Tesla, it gives priority to different tasks. So what do you think the priority is for the autopilot if it's running?
Cameras. Cameras,
Sorry.
the cameras to sense.
No, like, well, is it high priority, low priority?
Oh, Viper.
So the operating system will give that task very high priority. Whereas something like the battery level sensor, like, do I need to update the user interface on the battery level every 2 seconds? Right? So that would be lower level. So you would be designing that as part of the software for the operating system. And it's also going to be managing your resources. So what is going to be running on the CPU at a given time, which program that is part of that embedded system gets to run on the CPU. Things like that. Yeah, so that goes back to scheduling. So priority of tasks. How long does a task need to run in order to make sure that it meets its real-time deadline? Because some of these systems are very critical, right? Like a plane, they also have autopilots. They are an embedded system. You want to make sure that any real-time deadlines that are on those systems are met. Right? So the operating system is what ensures that these things happen. So there's a widely used operating system for embedded devices with real-time needs specifically. It's a real-time operating system, very clever name. Right? It's open source. So we don't cover that in this course, but it might be something of interest. Say after you take this course, plus you take operating systems, you could learn about it. All right, so we talked about integrated circuits. So this is an electronic circuit made from semiconductor devices on the surface of a thin semiconductor material, right? So this is a real chip, and it doesn't have the usual like coating over it to protect it. So this is before that was applied. So you can really see the different components of the integrated circuits. But this goes back to the key skills that we need to learn as computer engineers, right? So electrical engineering, what do we need to know in order to create the circuits?
The logic.
Digital logic. What else do we need to know? So we definitely need to know signals and systems in order to interface with different devices from this chip. But in terms of making the chip, what else do we need to know? So digital logic, you're talking about like AND gate, OR gates. But we also need to know digital logic circuits. Yes? So that is most likely something that none of you guys have learned yet, right? Like what does a transistor actually look like? How does timing work for a transistor? Right, that's usually a graduate level course. And that course is usually going to be labeled as VLSI design. So that's the electrical engineering side. What about the computer science side? What do I want to make sure my chip? What are the qualities of my chip that would make it a good chip? Do I want it to be slow? I want it to be fast. How do I know I'm making it fast? Yeah. So I need to know on what kind of applications is this chip going to be running? What are the common algorithms that would be running on it? Should I make more dedicated hardware for those algorithms? Like, if we go to the vending machine and the washing machine example, and say we're designing a chip for it, do I need floating point instructions on this chip? Probably not, right? It doesn't need to be that precise, most likely. So knowing about that in the design process, what are the programs that are going to be run on the chip? Right. So designing these integrated circuits. So we talked about this a little bit. So the design process for creating the integrated circuits is called VLSI. So very large scale integration. And that is because there's billions of transistors on these chips, right? So there is a undergraduate level VLSI course here that Reza Kamali teaches, I believe. So if you are interested in that course, it is available through electrical engineering. So CPU design is a VLSI process. Yes.
What's the name of the course, sorry?
It's the name of the course is VLSI. The course number, I have no idea. What else is a VLSI design process? So motherboard is actually not going to be VLSI. It's actually not that large scale because a motherboard has maybe hundreds of components, not billions. But that would be more of circuit design, analog circuit design from the electrical engineering side. What else that we talked about would be a VLSI design process? GPU, yes, those are also made from transistors, right? And they're actually quite a bit larger than CPUs. They're usually, in terms of die size, 4 to 5 times larger than a CPU. So we have some time. So actually what I want you to do is with the people near you, look back in the slides about maybe what we talked about. That would be VLSI design.
It's like, I would like that goes on.
I guess what you have to. Very well. Yeah, so you kind of.
That absolutely.
That's why. Yeah, but then I don't remember what it's for.
Yeah, that's.
Yeah, so probably because that's compromised, like. The valuation test.
Yeah, good engineers, that's what I'm.
Yeah. Good smart. They just. Yeah. Stop, take like basically the same class. I'm all the coding class.
Over.
CS lab.
I'll take it.
Oh. Oh. You're okay. It's an honest mistake,
Yeah, I get it.
especially when you come in late and it's the second day.
Yeah, I remember, like, every year in high school, I would always get the wrong class. I don't know why. I can never figure it out.
Like the first semesters were in class.
Oh, quick question. So you said we were gonna do HDL last semester. Are we gonna do this semester? Like,
HDL?
that's what you said, something like that. It's like, when I asked you if we were gonna do Arduinos, you said we were gonna do like the night, but like, that changes the circuit, like a programming language. Or was it BBL? Something.
Are you talking about like long time ago?
Yeah, like right after I finished my final exam.
Okay, so I have removed that.
It's what? Oh,
One unit class.
okay.
It would be too much to teach you guys Arduino on hand. It would be VHDL. And HDL is hardware designing. Actually, a way to model digital logic circuits as a computer language.
Okay.
Okay, so I think you guys have had some time to talk about this. Do we have any ideas about what we had previously talked about would require VLSI design?
Our guess was embedded systems, because you wanted to do one thing very well. So it's kind of like, they're the dedicated system, the dedicated embedded system. That was a guess.
Okay, so what component of an embedded system would require this VLSI design if it was only doing one function?
A sensor?
Not a sensor. A sensor is, because VLSI, remember VLSI, we're talking about billions of components. A sensor can be relatively simple. Like some sensors are just like a potentiometer, like temperature sensors. It just changes the resistance of that material based on the temperature, and you have a lookup table. So it's just like one component. So CPUs, right? CPUs can be part of embedded systems. We talked about GPUs. Right. So what else? I want to focus on how you said it does one task. One task. So CPU does and is capable of doing an infinite number of tasks, right? It's Turing complete. It can do anything. But if we wanted to do one task, be very efficient at it, what do we make? Starts with an A. Now, ALU actually does multiple things, right? Like it does add, multiply. So we wanted to do one thing. Said that lots of people bought this kind of thing. Maybe not regular consumers.
Oh, the accelerator.
Yes, accelerators. So accelerators. So application specific integrated circuits would be made through VLSI design. So rather than implementing a data path that has, say, an ALU and is programmable, can do many different functions, an application specific circuit implements a data path that does one function. Okay, we'll implement maybe one algorithm, and you cannot change it because it is physically sketched in on the semiconductor material, right? So the ASIC that we talked about was Bitcoin mining, right? So, and you can find them very cheap now because they're out of date. Yeah,
Oh, what does it mean, now with the end of Moore's law?
yeah, we'll talk about this. So this is a very large and growing segment in the market because CPU design is on a decline, right? Because CPUs, we were able to make them say 30–40% faster every 2 years for the past 50 years, right? Because we were able to fit 30, 40, 50% more transistors onto CPUs because of technology. Yeah.
Aren't they getting like so small to where they're almost like, they are microscopic?
Yeah. So
Getting so small that they can't really make anymore.
yeah, so they're at the point at 3 nanometers where they're so small that a single transistor is only consisting of a few atoms and it's becoming unpredictable behavior. So it's not working as a transistor. It's unstable. So because of this, we cannot fit more transistors onto the chip. So because we can't fit more transistors, we can't make faster processors, more efficient processors. The other thing that came with smaller transistors was they were more efficient. But we can't make them any smaller. But what does the consumer want in order to buy a new computer, a new laptop, new anything?
Thinner, smaller.
Faster.
It needs to be faster. It has to be faster. There has to be some new thing that makes it better. But we can't make it simply faster or more efficient with Moore's law anymore. So we need to create these ASIC designs as accelerators to make it get better performance than the previous generation. So an example of this is the TPU that you talked about, right? So TPUs are an accelerator. They are generally run on the server level, like in some server farm in the middle of nowhere, usually, right? But they also sell TPUs to consumers. You can get Coral chips, and you can run those applications. There's some that are just ready built. Like you can do object detection, things like that. Say you have a security camera system in your house, right? You have those camera feeds. You can feed that camera feed into these algorithms that would run on the TPU. TPU is much more efficient at doing this task. The Coral TPU is running on the order of milliwatts in terms of power, but a CPU running the same, like say, deep neural network that is implemented for this object detection. What do you think a CPU runs at in terms of power? What wattage? What scale? How many watts?
Gigawatts.
Not gigawatts. Gigawatts, which
That's a lot.
that's a lot.
Kilowatts?
Not kilowatts, that's still too much.
Watts.
Yeah, generally what, like usually 65, 150 watts is the CPU. Yeah, and then on the CPU, how long do you think it would take to run a neural network inference? On the order of minutes, I'd say minutes on the CPU. So we're at milliwatt, so 1,000 times more efficient, right? And inference for it, seconds. Not even seconds, milliseconds. So in terms of efficiency, if that is the application that you want to accelerate, then you need this ASIC design, okay? So there was someone that was a computer engineer working on this, the whole team, but you get what I mean, right? And that's just one example of how ASICs are becoming more widely used.
They look like CPUs or
They look exactly like a CPU. Like from the outside, it's just a chip.
Coral's tiny. It's like a USB stick.
Yeah, you can get it in USB stick form. There's an M.2 form factor. They have PCIe cards. So the main difference between like the USB stick and the M.2 form factor and the PCI card is how many TPU cores are on that chip, usually. So where was I getting to? All right, so that's one example, right? So there are other examples where we are seeing ASIC chips being made. Another example is on your phones. No matter if you have an Android phone with a Qualcomm chip, a Samsung chip, or Google's making their own chips now, right? Or you have an iPhone with Apple's chip. Almost all of those chips, they have the general purpose CPU on them, right? You need that in order to have it be programmable to do any function. But they also have an accelerator that is similar to the TPU. Because what they're using this accelerator for is, what do you think?
Speed.
Yes, speed, but application. What application do you want to run on your phone? That would require something like a TPU.
Oh, cameras?
So cameras are actually that's a good one. So digital signal processing is possible. I don't think they use a application specific circuit for this though. But it might be true for Apple because they have the AI,
Yeah.
like what is it?
What's a filter though?
Yeah, the filters. So it could be true. I don't know this answer though, but I do know the answer to the other thing.
Video decoding.
Video decoding is just run on GPU. Do you talk to your phone?
Speech recognition.
Yeah, so like your assistants. So Siri, Google Assistants. Okay. So they're moving more and more of that processing from servers, I'll get to your phone. Okay? Because what they have done before was they only implemented enough hardware in order to just detect the initial dictation of Hey Siri, okay Google. And then they would send the dictated real message to a server for processing. But what does that mean about your data?
So it can get stolen. Stuff.
Right? So I mean theoretically it's encoded, it's encrypted, right? But it's still going to some third party, maybe not third party, but some outside source that's not your own device, right? So users, as they're becoming more knowledgeable, they want more privacy. And what else is the problem with sending data to some server farm like thousands of miles away? Well, it could be intercepted, but what's the other main problem? Yeah. So it takes time to send it there, takes time to get sent back. It's not instantaneous. But if you have the processing on the phone itself, it's much closer to instantaneous. Okay. So this is a growing field. Your question.
So in general, are like tech companies moving to like making their products with just like a general purpose CPU and then concentrating more on that accelerator part side?
Yes. So they have accelerator teams. Like I have an example I can give you of. So when I was at UCSD in the PhD group, not everyone goes to academia, right? So some were more focused on software and like being good programmers, right? But if any of you have tried to apply for an internship for programming, how many people are out there trying to do the same thing? How many companies even get back to you, right? But we also had people in hardware design and ASIC design. How many people do you know want to be an ASIC designer? None, right? It's a very difficult field, but it's also the growing field. So programmers, like stagnating, ASIC design growing. So everyone that I know that was coming out and applying for ASIC design jobs, much easier to find a job. And they're at the same companies. Like at Apple, the people making the whatever they're on, M3 chip was what they should be finishing or have finished and just haven't released. And they're working on M4, right? They need people with these skills to make those accelerator parts. There are already existing people, maybe senior people, that were more focused on general purpose, but they need more application specific. Yeah.
Do you have any classes on that? Yeah or no?
Yeah, it's the VLSI class.
Okay, so it is a BS.
Yeah, so the VLSI class will give you the kind of base knowledge that you need. But usually it's a graduate course that will get you the rest of the way there and you'll be able to then do those interviews after you take the graduate level course. But I just wanted to highlight that this is a very strong career path, I think, nowadays.
Do you get any offers from private PhD?
I didn't apply to anything but academic positions. But I know people that were applying to those other positions. Okay, so we are out of time, but I do just want you to answer the question. I know you guys will get this right, so I'm not worried about the peer instruction part. The code is 963. And I will leave this open, so like if you have another class to go to, you can just get up and go. I'm not going to
They
close
gave
it.
me this. They also gave me this last one.
Can you go back? There's a 960. I know you're here.
Okay.
Just, when I run the script, it won't catch you.
Huh.
So when it posts the grade to Canvas, just tell me however you want to tell me, Piazza
Yeah.
or email, and I'll just change it.
Does the first class count? Or no? That's just.
Wow. Just 1 second, let me just sign out here.